In this problem, we want to start with a cylindrical can. So we have our picture here of radius r and height h. So we have a cylindrical can that's made to behold a fixed volume V. So we've got some fixed volume V. We want to find the dimensions that will minimize the cost of the metal to manufacture the can. So let's write down our key ideas here. We have that r is the radius and h is the height. Our constraint would be that, so our constraint is the volume is fixed. It's our value V. And we want to minimize we want to minimize the dimensions that will minimize the cost of the metal. Well, the cost of the metal is fixed, so it's just how much metal we're going to use. So really, the metal used is the surface area. So we want to minimize the surface area of the can. So this is what we need to do. We're going to minimize the surface area of the can. We've got the constraint that the volume is fixed. R is radius, h is height. Of course, we don't have any equations yet to do calculus with. So let's start off with what is volume. So volume, we know, is of a cylinder. Well, it's the area of the top times the height. If we just took the area of the height and added it all up, that would be multiplying by h. And the area of a circle of radius r is pi r squared. So we get that the volume has to be pi r squared times the height. So that's our volume, and that's going to be our constraint, because volume is not a variable, it's a constant. So we know that pi times r squared h has to be some fixed number volume. Now, how about surface area? Well, let's kind of take this into pieces. Again, we know a can is composed of at least 3 different components. We've got the top, which is a circle of radius r. We've got the bottom, that is a circle of radius r. And then the side, if we were to just snip down the side and open it up, it's actually a rectangle whose height is h, and its width, well, it's got to run along the circumference of the circle. And the circumference of a circle is 2 pi r, so the width would be 2 pi r. So the surface area would be the area of these 3 things added together. So let's give another variable. Let's say S is surface area. And so we have that S is equal to, well, 2 circles, and their area is pi r squared. So 2 pi r squared plus the area coming from the sides, which is 2 pi r h. And this is the surface area. This is the function we want to minimize. And as we do with all these problems, we've got too many variables. We've got an r and an h. So we use the constraint to solve for one in terms of the other. And it seems to me that it'd be easier to solve for h here. So we get that h is equal to pi r squared, let's do math correctly. How about h is equal to v divided by pi r squared? And so then this tells us that our surface area, S, is equal to 2 pi r squared plus, now when I put v over pi r squared into here, the pi's will cancel, and one of the r's will cancel. So I end up with 2 times the fixed volume. Remember, that's not a variable, that's a number, divided by r. And since I'm going to do derivatives, I'm going to use the negative exponent. So that's our surface area. So in all these problems, we know that we now want to minimize this function, and we'll do that by taking the derivative. So what is ds? Well, ds is equal to, so power rule, this is equal to 4 pi r. And then we've got power rule again, the negative comes down, so this becomes a minus 2v r to the negative 2. And I forgot my dr. And so then ds dr is equal to 4 pi r minus 2v r to the minus 2, or putting this into rational form under one common denominator, r squared, is going to be 4 pi r cubed minus 2v all over r squared. Okay, so this is our derivative, and we want to know when is this equal to 0, or of course, when is it undefined? Well, the derivative is undefined when the radius is 0, but since in this application, we know that we're in a real world, so we could have put on here that another constraint that didn't say explicitly, but is very implicit in the problem, is that our radius has to be greater than 0. If we have a 0 radius can, well, it can't possibly have any volume, and so it's impossible to solve. So our radius has to be bigger than 0. So the place where the derivative is undefined is outside of our domain. So we only have to worry about when is the numerator 0. And so when is this 0? Well, this is 0 when 4 pi r cubed minus 2v is 0, which tells me that r cubed has to be v over 2 pi, or solving for r has to be the cube root of v over 2 pi. All right, so that's our critical value. Is that critical value a place where the surface area is minimized, or is it where the surface area is maximized? We just have a critical value. We don't know whether it's a min or a max. Well, I could take the second derivative, put this value in, and try to determine if it's negative or positive using the second derivative test. And that's quite doable. Though I look at this, I'm like, well, there's going to be a lot of work trying to differentiate this, and then I'm going to have to evaluate, and it may be a little bit cumbersome and difficult. So instead of going that route, I'm going to use the first derivative test. I'm going to look at the value of the derivative before and after this critical value. So, if r happens to be less than my critical value, we know the critical value makes it 0. Well, if it's less, then I can cube both sides. So r cubed is less than v over 2 pi. And then I can get rid of the 2 pi here. So in fact, this is if and only if. So if and only if 2 pi r cubed is less than v. And let's come back up here and look at our function, kind of get a sense of where we want to go with this. Our function that we're trying to determine, is it negative or positive, has 4 pi r cubed minus 2v. Well, this is almost there. This is 2 pi r cubed, and then minus some stuff. Well, if I multiply both sides, I'll at least get the 4 pi r squared. And so this is true if and only if multiplying both sides by 2, that 4 pi r cubed is less than 2v. And of course, that's true if and only if 4 pi r cubed minus 2v is less than 0. And notice this is our numerator in the above function for ds. And the denominator is squared, so it's always positive regardless of the value for r. And we know r positive anyway. So what do we know? Oh, well, if r is less than our critical value, then the numerator of our derivative is negative, which means the whole fraction is derivative. So whole fraction is negative. So this implies that ds dr is less than 0. On the other hand, by almost an identical argument, if r is greater than cube root of v over 2 pi, I would do the exact same thing. I'd cube it, multiply by 2 pi, multiply by 2, and then subtract, and I would get if and only if 4 pi r cubed minus 2v is positive, which implies that ds dr is positive. So what does that mean according to the first derivative test? Well, we know that so if r is less than our critical value, the function is decreasing. So S, our surface area, is decreasing. So if we kind of look at the number line, here's our cube root of v over 2 pi. We know it's decreasing, and after that, because the derivative is positive, the surface area is increasing, so we must be, by the first derivative test, at a min. By the first derivative test, S is minimized at r equals cube root of v over 2 pi. All right, we found the minimum value for the radius. Are we done? Well, the problem says let's find the dimensions that will minimize the cost. So we need to find both r and h, and we can come back to our formula for h here. We know that h equals pi r squared. So let's come back down here. And so recall that h is equal to volume divided by pi r squared. And I could put this into the problem, square it, and do all the algebraic manipulations and kind of see what h has to be in terms of r. But I'm going to do kind of a little trick here. The biggest reason is I look at here and I say, oh, r is being cubed, or cube rooted, but here r is being squared, which means I'm going to end up with a bunch of two-third powers, and I'm not crazy about that. But if I divide both sides by r, which I can because the radius is not 0, this tells me that h divided by r is the same as v divided by pi r cubed. That's going to be nice, because if I put the value for r in there, which is cube root of v over 2 pi, this is equal to v over pi times, well, if I cube the cube root, all that gets left behind is v over 2 pi. And lo and behold, all sorts of stuff start canceling. So the pi cancels, the v cancels, and this 2 is in the denominator. So this is just equal to 2. Oh, what does that tell me? H divided by R is 2, or in other words, H is twice the radius. Now, we know the value for radius, so this is just going to be, if we had a fixed volume, this would be 2 times the cube root of V over 2 pi. But there's something incredibly powerful of what we just discovered here, that this relationship between H and R is, how do you say, doesn't regard even the value of the volume. Remember, we started with some unknown volume, and we found out regardless of the volume, that, I mean, of course, H has to be 2R, and then you could solve for R and find out what the radius has to be for some fixed volume, but the relationship will always be that the height is going to be twice the radius. As long as that's the case, then the surface area will be minimized. And let's even stare a little bit closer about these things. What is R? R is the radius of our cylinder, and 2R is the diameter. So what it's declaring, that if I want to minimize the volume of, minimize the surface area of any can of fixed volume, then it's going to be kind of a square-shaped can. Its diameter will be the same as its radius, its diameter, so 2R, will be the same as the height. So a can that minimizes the surface area for some fixed volume will always have the relationship that its diameter and height are the same. Good to know if you're ever out there having to develop cans and you want to minimize the surface area.